So we're going over in this video the S2 Edexcel June 15 paper. The first question, clear Poisson distribution, because it talks about the rate per 1,000 kilometers squared. So we're definitely dealing with Poisson 9 for the first question. So it just says that what is the probability of there being at least, so here we just have to be a little bit careful with the inequality. That means at least 10, that means it can be 10. Remember, Poisson's discrete, so it can be 10, 11, 12, so on. So that means probability that that our Poisson distribution takes values of greater than or equal to 10. And then what we can do, remembering it's a discrete distribution, that's 1 minus the probability that x is less than or equal to 9, because that's basically all the possibilities, 0 up to 9 are not included, so we're just taking those from 1. So that is a case of, now because it's Poisson 9, we can look those numbers up in the table. So let's have a look at that, the cumulative numbers. Because the cumulative numbers go up to when the inequality is in that direction. So let's just go to the tables now. So here I am scrolling through the formula book until I get through to the relevant page. Going through all the binomial ones there. Here we go. Still binomial. And finally we come on to Poisson on page 26. Now it was Poisson 9, less than or equal to 9. So it's 0.5874 is the number we're looking for. So that's 1 minus 0.5874, which equals to 0.4126. We can leave in 4 significant figures, you don't need to round. Okay, so that's that, part A. Let's look at part B. And part B is also Poisson, but of course the actual area is changed, because you'll see we're dividing by 5. So we're going to expect a factor of 5 fewer owls in that particular region, because it's about barn owls. 1,009 per 1,000 would be the same as 9 divided by 5 per 200. Which is 1.8. So now we're dealing with Poisson 1.8. So now we have the probability, and it wants, that's not a number that it does occur in the tables, but thankfully it just wants exactly 2. So we want the probability that x equals 2. Okay, so just putting that into the formula. For the rate is e to the minus lambda, and lambda is 1.8. And then it's lambda, which is 1.8 to the power of the number of occurrences, 2, over 2 factorial. Okay. And that goes to 0.2678. Okay, incidentally, talking about for those who do mechanics, stats papers looking at the mark scheme, they seem to be often okay with 4 significant figures or 3. But I think, I haven't looked at the mark scheme, sometimes you'll see the term anything which rounds to in a mark scheme, which rounds to AWRT. But I know that 0.2678 will not be penalised for over accuracy, so that's fine. Right, and then it talks about the part C is an approximation, and it's because what happens is we've got the rate changing again, but this time it's actually 1,000 times 50. So we've now got Poisson of 1,000, not 1,000 times 50, 9 times 50. This is times 50 here. So the number of owls in that particular region we would expect to be 50 times more than there is per 1,000. So it's 50 times 9, which is 450. Now, of course, that's not a number that we can deal with because it's so big with either tables or the Poisson formula. So we use the normal approximation. When we're dealing with Poisson, there is only one approximation that we can use in S2. So Poisson can only be approximated to normal. But because this is Poisson is discrete and normal is continuous, we need a continuity correction. So we need to watch out for that. Well, I'll tell you when it comes up. Okay. Now, what we can first of all do is say y, it's approximately the same as y, let's call it normal distribution, with mean 450 and variance 450 as well, or standard deviation the square root of 450. So we're going to use this to approximate this. Okay. So now let's look at what we're asked to approximate. 470 barn owls at least. So the word at least, that means 470 or more, because it can be 470. Be careful with wording here. Had the question said more than 470, the inequality would change. But we want the probability that x in this case is at least 470 or more. So we have a non-strict inequality like that. And we're going to approximate to this to our y distribution here. Now here's where the continuity correction is. It's going to be probability that y is greater than or equal to 469.5. So that's our continuity correction, because the way we do it, if we've got a non-strict inequality like that, that's why I always convert to that when I'm dealing with, well, any discrete distribution, to be honest. Then we've got 470 is the number on the number line that we could go, and it'd be greater than. The continuity correction always extends it further than the number line, so we go half backwards. So if it were the other way around, we'd go half in the other direction. So the continuity correction always kind of extends beyond that one. So we've got 469 there, 470. So it's always going a little bit backwards from the line, but only if we change. That's why I say always change to a non-strict inequality like that. So there we go, that's the continuity correction. So now we're going to transform to the z distribution. So probability that z is greater than or equal to, now we want 469.5. Take away the mean, which is 450. Divided by the standard deviation, which is equal to the square root of 450. Okay, so now working this number out on the calculator, I'm getting 0.919238 and a load of other stuff, but I know the tables only go to 2 decimal places, so, and it's pretty close to 0.92, so you're never asked to interpolate or anything in S2 or S1. So that's z is greater than or equal to 0.92. Now we're on this side of the bit here. Z is we're looking for that with 0.92 there. So we need to do 1 minus. I'm a bit lazy with the inequalities now because I'm dealing with the, well, it doesn't really matter whether I put strict. Once I've gone to the normal, the nature of the actual inequality doesn't really matter. But it's absolutely critical for a discrete distribution whether we've got strict or non-strict. Anyway, let's go to the tables to look for this number. So remembering that the S1 formulae, because we do normal distribution in S1 with Edexcel, so we need to scroll back to the, there we go, 0.92. Here it is. So the number, the actual psi value we've got is 0.8212. So let's return back. So that's 1 minus 0.8212. 8212 come to 0.1788, or anything which rounds to 0.179, which is what the mark scheme says. I do find that with tables they seem to be happy with four significant figures when tables are used, because the tables are given to 4 significant figures. Anyway, let's move on to question 2. So, next question. The proportion of houses in Radville which are unable to receive digital radio is 25%. And then it talks about 30 houses. So this is really telling us that we're dealing with a binomial. We're dealing with binomial with 30 trial, 30, a sample of 30, and probability success 25%. That's actually success in this case is kind of failure in a way, because it doesn't really matter. 25% is the number of people who cannot get digital radio signal. Okay, it's not necessary to change it to 0.75 so that you've got probability of success. It's really mathematically it makes no difference. So we're being asked for the probability that x is less than or equal to 5 but less than 11. Now, first things first, let's deal with this inequality. As I said with Poisson just in the question before, it's a discrete distribution. We really need to be careful with inequalities. I prefer to work with non-strict inequalities, so I'm going to change this inequality here. That means if it's going to be less than 11, it means it can be 10. It can be equal to 10, so it's less than or equal to 10. I have had some students who are quite happy to work and switch between both and just go to the calculations, but I've also had many more who make mistakes, and I confess sometimes I do too, so great care is needed. Right, so that means the probability that x is less than or equal to 10, because that's all of the 10, all the way 10, but then of course that would include the numbers from 0 to 4 as well, but not 5. So it's take away the probability that x is less than or equal to 4. I mean, if you want, I mean, it's probably, hopefully it's not necessary. You can write the numbers down and we can kind of see. Don't have to write them all, but you can 3, 4, 5, and then up to 10. You can see, well, we want 5 to 10, so we're taking these ones away. Okay, so I mean, probably not necessary to do that, but you know, if you have to, rather than make mistakes, it's important that we do. Okay, so now we can look at the numbers for 10 and for 4. Right, in these first few questions we really are working through the tables. We've used normal, we've used Poisson, and now we're using binomial, but binomial with 30 trials. 30 trials, and we're looking at the two numbers we're after are, and probability. We can't see the probability, but I need to be looking in this column here. So that column there. So the two numbers we're after are for 10, 0.8943, and for 4, which is 0.979. So let's return to the main sheet and write those down. So that's equal to 0.8943 take away 0.0979, which equals to 0.7964. Okay, part B is about a significance test. It says a random company claims that a new transmitter will reduce the proportion. There's a key word there, reduce, not change it, reduce it. So it's going to be a one-tailed test, which are unable to receive digital radio. After the new transmitter has been set up, a sample size of 15 houses is taken, of which one house is unable to receive. So we've actually got the value of a test statistic. When you're given the value of the test statistic here, you've given a particular result of some survey or some kind of finding, some value. It's normally easier to test that value than to work out the critical region, I would say. So although you can use critical region, I'm not going to here. So again, we're dealing with binomial, but of course the number of trials now is 15, and it's hypothesized. The H0 is that it's unchanged, so let's write that down. 0.25 for H0 is right. But let's write out the actual hypothesis that H0 is that P. I don't normally write equals, do a little dot dot. P is equal to 0.25 is unchanged, and H1 is that it's reduced, so it's going this way, 0.25. And what we do is we assume H0. Okay, we assume what H0 the value of H0, and see what that comes up with. If it's actually very unlikely that happens and below our tolerance level, our significance level, then we reject H0. So we just do a bit of work with probability, assuming that there is no change, assuming H0, and see what happens. So here we go. I do like to use the language of conditional probability, certainly on the first line here. So we can say probability that X, now our test statistic is 1, but don't test exactly 1. You've got to test something less, not just 1. You've got to allow for the possibility of something even more unlikely, something even more remarkable than the value of our test statistic, and that's 1. Given, assuming that P is equal to 0.25, you don't have to write that, but it makes it clear what we're actually doing. We're assuming that H0 is the case, then what's the probability that X is less than or equal to 1, given our values? Now, because it's actually the direction of the inequality is quite helpful, don't really have to do much now, but to actually just go straight to the tables to find for a gain binomial. So we're going to go back to tables with 15 and 0.25 and look for the cumulative value of 1, which basically gives us the 0 and 1. Of course, you could use a formula here because you have to do it twice, but it'd be quicker to use the table. So let's go to tables again. So we want 15, we want the 15, 0.25 and 1. So this is the value we're looking for, 0.0802. Okay. So that's equal to 0.0802. Now the key thing is here, it is quite unlikely, well, 8%. We've got, that does fall below our 10% tolerance. Okay, so we do need to come to that conclusion. And we need to conclude now. So we say something like, now we have to do it in context, but the first thing to say is reject H1. Reject H0, of course, accept H1. Don't have to say both, I don't think, but I'm going to anyway. And we need to give a statement in context. So I like to use the same kind of phrase. There is sufficient evidence to, and just let's have a look at the actual thing. Has been said. That which one has it? A radio company claims So it's talking about a radio company. To evidence to suggest radio company's claim is true. Claim is true. Now that's probably enough. I'm looking at a mark scheme. That's actually sometimes gets the marks in itself. I think we need to be they normally give that as an alternative, but I'm going to use both just in case. So we can also then say that is the number of houses which are unable to receive a digital signal is reduced. I probably kind of tick the box twice here, but I think it's better to do that than it is to not tick it at all. So I think probably I've ticked a box there and there, but I do worry sometimes that they might change their stance on this. I'm not an examiner, so you never know. That will definitely get it anyway. Okay, let's look at the next question. So question 3 is a continuous random variable question. We've been given a PDF and we use the fact that the area under PDF is equal to 1. Quite important because one of the numbers, something's going to happen between 0 and 6. Area underneath is equal to 1. Equals 1. That's the thing we're going to use, but this thing is broken into 2 bits, so we've got 2 bits we've got to integrate. So we've got k times x squared dx integrated between the limits 2 to 0 plus k times 1 minus x over 6 dx integrated between 6 and 2 equals to 1. This is a case of being working through this integration and getting an answer for k, which they've given, thankfully, so we know what we're heading for. So x squared integrated is x cubed over 3 between 2 and 0 plus 1 integrated is obviously x, and x over 6 integrated is x squared over 12 between 6 and 2, and that equals to 1. Right, now this bit here, the 0 limit is just going to be taking away 0, so that bit there is just going to be k times 2 cubed over 3. This bit here, we've got 2 bits k, 6 minus 6 squared over 12, take away k, 2 minus 2 squared over 12 equals 1. So we just need to take a little bit of care, and hopefully we'll get to where we need to go. Okay, so this first term here is 8k over 3. Then we've got plus 6k. The 6 squared over 12 is 36 over 12, which is minus 3k. Then we've got minus 2k, but then it's plus 2 squared over 12, which is 4 over 12, which is equal to 1/3 times k, or k over 3, which equals 1. Now bringing all this together, these are whole numbers there, that's just equal to k. And these two together equal 3k, so that gives us 4k equals 1, so k equals to a quarter as required. Okay, now that's part A done. Now part B is just a 1 mark question. If ever it says write down, it literally means write down. The highest point of a PDF is what we're looking for. Now I'm going to draw a graph in a minute. It's not really necessary. This is going to be this is increasing. And this, because of the negative gradient here, is decreasing. So we should be able to see that the mode must be, because it's the highest point, if it increases then decreases, then it's going to be the highest point, which is 2. So we've answered the question. The graph of it is, well, just because I was working through this, I think it might be worth mentioning. It's a bit strange in that what happens is, not that strange, but it is a little bit unusual in that we get the quadratic, we've got the quadratic bit up to 2, and you might think, oh, the rest goes like that, because we see a lot of PDFs like this, but this one looks like it's broken, because when I put 2 into there, where there we get the value of f equals 1, but then when I put 2 into this bit, I get some number less than 1, I think. Yeah, it's a quarter, that's 1 that's 2/3, a quarter of 2/3, which is less than 1. So it's actually doing something like this. And you can have broken PDFs like that. It is a bit unusual. So someone who actually tried to put a bit of thought into it might get a bit confused. But yeah, this is increasing, this is decreasing, so therefore the mode is equal to 2. Okay. Right, so now, sorry, I said part C, but that's part B. Right, part C. So we're going to integrate. Now, we know that k is a quarter now, so we can assume k is a quarter. So let's look for our various bits. So let's deal with the 0 to 2 bit first. So we're basically integrating. And I know that some people put limits on here, but I prefer not to and just work out the constant. So if you want to put limits, go ahead, but I prefer to, especially with a broken one like this, because how to put the limits on when you're working this one out can be, it just requires too much thought, to be honest. So anyway, it's much easier to work out the constant in my view. So we've got a quarter x squared dx. So that equals to 1/8 of, no, not 1/8, 1/12 of x cubed plus c. Okay, so I now can work out c, because I know that f naught equals to 0, because my lowest value is 0, and it's equal to 0. Now that's pretty straightforward. So I have 0 is equal to half a quarter, 12 times 0 cubed plus c. So obviously c is equal to 0. Not even worth writing, to be honest. So c is 0. So that's that bit. Let's deal also with the other bit, which is that with x being between 2 and 6. So now we're integrating a quarter between 6 and 2 of 1 minus x over 6 dx. Okay, so that will be equal to a quarter times x, because that's that bit integrated. This bit integrated is x squared over 12. But we've got, we're dividing that by 4, so that's x squared over 48 plus c. Okay, so those are our, so those are, now to work out the limits, it's now easier, I think, to work out the fact that 6 certain to be some number less than 6. So we use the fact that f6 equals to 1. So we have 1 equals to 1/4 times 1 minus, times 6, sorry, because it's our value, minus 6 squared over 48 plus c. Okay, so that gives us 1 is equal to, the 6 over 4 is 3 over 2. 6 squared, 36 over 48 plus c. I want to use a calculator really. So 36, so if I divide those by 12, I make that to be 3 over 4. So I'll get 1 is equal to 3 over 2 minus 3 over 4 plus c. So that gives me that c is equal to 1 minus 3 over 2 plus 3 over 4. Putting all those over a common denominator, 4 minus 6 plus 3 gives us 1/4. So that gives us fx within that range equals 1/4 x minus x squared over 48 plus 1/4. Right, but it does say, if we go back to question, we can't just write the functions. There's 5 marks here available, so we need to fully specify it. That means fully define it. So we have our fx going between, now we had our 3 bits to it before, so it's going to be 4 bits to the PDF. That's 0 if x is less than 0. Okay, that's clear. We can't have any numbers less than 0, so 0 probability there. Then we've got this part of the rule, but with c is equal to 0, so that's 1/12 x cubed if x is greater than or equal to 0 and or less than or equal to 2. Okay, and then we've got this part of the rule between 2 and 6. So we've got 1/4 x minus x squared over 48 plus 1/4 applies between the values 2 and 6. And then 1, if we have, it's certain, any number, because it's certain that we have a number less than 6, the cumulative value above that is going to be any number. It's also certain that we have any number. If we put 7 into there, it's also 1, because of course it's certain that the number is less than 7, and so on. Okay, so that's that question done. Not the whole question. Now the part D, it says find the upper quartile. Now in this case we might be thinking, well, I don't know which one of these to look into. You know, is it in here? We've quickly put 0.75 in there. You'll find you get a number outside the range. So it's just, sometimes you just have to try it, but it's actually this one. It feels like it would be in that one because it's higher up, it's 0.75, but it wouldn't be absolutely certain. It could be there, but it isn't. Okay, so if you put 0.75 as half x cubed, I might as well do it now, I've alluded to it. This is not going to yield to anything, because that would give me 12 times 0.75, which is that, and the cubed root of that is equal to 2.08, which is outside the range for which that will apply, so therefore it's not that rule. Okay, so it's here where we're putting our value of 0.75. So here we go. 1/4 x minus x squared over 48 plus 1/4, I'm going to write it as a fraction, equals 3/4. So I might as well use the notation we want. So I can call that Q3. is what we're looking for, the particular value when it's for the upper quartile. So I'm going to times through by 48 here. So if I times by 48, I will get 12Q3 minus Q3 squared plus that times 48 will be also equal to 12 equals to 36. So that gives me Q3 squared minus 12 Q3 plus 24 equals 0. So Q3 using the quadratic formula will be equal to 12 plus or minus the square root of 144 minus 4 times 1 times 24 all over 2. Right, now this quadratic equation leads to two solutions, of course, as normally does. So one of them's over 9 now. When we add the two, it's over 9.46 or something of the like, which is not relevant because of the range. 9, it's obviously, the rule applies somewhere between 2 and 6, so we need the value to be between 2 and 6. So that comes from the actual subtracting option here. So rounding that, I get the answer 2.54. Question 4 starts off with a continuous random variable, which is a continuous uniform distribution, and it's talking about errors in measurements, and it gives us the numbers can be anywhere between 0 and 0.5. So basically, it's sometimes called a rectangular distribution, looking like that, going anywhere from 0 to 0.5, and the probability that L is less than 0.4. Well, that's clearly less than 0.4 is this number here, and we can see that's 0.8 of the area because it's 4/5 along. So probability L is less than 0.4, no need to use a formula, it's obvious, the answer is 0.8. EL, again by symmetry, we can see that EL will be halfway along here. By symmetry, the mean EL will be halfway along there. I'm struggling to write it there, but the mean will be halfway along. So EL equals to 0.25 because it's halfway between 0 and 0.5. Right, part C, there's a formula for the variance, particular for the continuous uniform distribution, so we don't have to use integration where we x squared fx, which we could do, it wouldn't take that long, but even quicker is to use a formula that's in the formula book, which is for the continuous uniform only, which goes something like this. Yeah, so that's 0.5 squared over 12, and that comes to 0.48. I believe. No, 1 over 48, 0.48. And that, if we to change to a decimal, I think 1 over 48 is fine, but is 0.208. 0.208, shall I say. Okay, so that's the first bit knocked off pretty quickly. Now part D is a little bit more involved. It says a random sample of 30 poles cut by this machine is taken. Find a probability that fewer than 4, that means less than 4, have an error of more than 0.4. So first of all, perhaps we better say the probability of there being an error of more than 0.4 is 0.2. And we're basically looking at the number of times this occurs out of a sample, this occurs out of a sample of 30. So it's binomial because it's a fixed number of trials, 30, 0.2. Now be careful with the inequality because, as I said before, it says fewer than 4, so that's probability that x is less than or equal to 3. Okay, so we need to find this number in our tables. So let's just go to the tables. So the inequality is going in the right direction for us to use the tables without any manipulation. So let's just go and do this now. So scrolling through the papers, we need to find 30 trials. Okay, and we're looking for the 0.2, this column, so the fourth column along. 30 trials and probability that it's less than or equal to 3, which is 0.1227. Okay, so let's go back to the page. So 0.1227. Okay, so let's just move on a bit. Now they've changed in the model a bit. So when a new machine cuts poles to a target length, the error is modelled by the cumulative frequency function here. This is cumulative, and it's a capital F. Use this model to find px is greater than 4. So here we've got px is greater than 0.4. So is going to be, we need to manipulate this because this gives us the probability of it being less than a certain value. So that's 1 minus p, x is less than or equal to 0.4. So that's 1 minus f of 0.4. So that's 1 minus 0.4 into here. So that's 4 times 0.4 minus 4 times 0.4 squared. I think that comes to quite a small number if I'm going to check. Yes, that's 0.04. Okay, so that's pretty easy, couple of marks. And then finally part F. It says a random sample of 100 is taken, so we've got x is binomial 100 and cut by this new machine. Using a suitable approximation, find a probability at least 8 of these. So we've got a binomial of 100 and 0.04. So we're being asked for the probability that x is at least, that means 8 or more. Now that's, this basically is going to be very hard because it'll take a while. We'd have to add together quite a number of values. But anyway, it says a suitable approximation. Because n is large, 100 I would say is pretty large, and p is small, where this really lends itself to the Poisson approximation. Because n is large, p is small. The normal approximation, we really don't want p to be small. So that's with NP is equal to the mean. NP equals to 4, 100 times 0.04. So NP is 4. So if we let Y be Poisson 4, this value is going to be approximately the same as, now there's no continuity correction here because they are both discrete distributions. So that's going to be the probability that y is greater than or equal to 8. And that's going to be equal to 1 minus the probability that y is less than or equal to 7. So now we need to find this number in the Poisson tables for Poisson 4. So let's go to tables again. So we've got Poisson 4 and we're looking for less than or equal to 7. And so the number we're looking for is 0.9489. Okay, so that's that question done. Let's have a look at question 5. The first part of 5 is a significance test, or it's talking about finding a critical region. So we're just being asked for the critical region, so we don't have to do the full process of finding, state in H0 or whatever. But it's clearly Poisson 4 because, well, there's no confusion there. It's Poisson 4 times a month. And it's a two-tailed test. So we're H1, H0, I'll write the H0 and H1 anyway, because it's a good idea. But then, mind you, it does tell us in the next part to do that, so I'll do it later. H1 is that it's two-tailed and that it's not equal to 4. So we're looking on both sides of the tail. So let's just have a look at the tables for the Poisson distribution and find some values and look at that. Well, on the lower tail, it's pretty clear that this is the number that we're looking for. The probability that x is less than or equal to 0 is equal to 0.0183, because this is much bigger than 2.5%. That's much closer. Okay, now on the upper tail, you've got to kind of take it away from 1. Obviously, these numbers are 2. We're looking at that one possibly. That one's too small, isn't it? Because this one itself, if I take it away from 1, is going to be slightly under 2.5%. And this one's going to be slightly over. Now, to be safe, I'm going to write the result for both of these, but I think it's going to work out to be the 8 that I'm interested in. Okay, so let's just write down those 3 bits that I've got. That, and the result for that, and what they represent. So there they are. Obviously, clearly this is in the critical region. And the other one, as we saw, was 0.09, x equals 1, so that's not critical. That one is not a critical value. A little bit of care needed for the upper tail, I suppose. Let's work with this one here. That gives us the 7.1. That's telling us the probability that x is greater than or equal to 8, let's write it. So 1 minus the probability that x is greater than or equal to 8 is equal to 0.9489. So that gives us a probability that x is greater than or equal to 8 equals to 1 minus that number, which is 1 minus 0.9489, 0.0511. That's 5%. Now, working on this one, we've got 1 minus probability that x is greater than or equal to 9, gives us 0.9786, which gives us a probability that x is greater than or equal to 9 is equal to 1 minus 0.9786, and that's 0.0214. That's the closest there to 2.5%. Okay, so that's the closest to 2.5%. So that's the one with that. So this one is almost taken away from our calculation. That doesn't give us our critical region. 8 is not a critical value because it falls above 2.5% and it's not as close to 2.5%. Because this question says close to, but in actual fact, it wouldn't have made any difference if it said it had to be below 2.5% in this instance. Okay, so let's move this around a bit. So that's telling us here that this is the critical value. Okay, so the critical region is x is equal to 0 on the left-hand tail, and x is greater than, and it's Poisson, so it's just open-ended, you can go to any number, is greater than or equal to 9. Okay, is our critical region for a two-tailed test. So part B, as I mentioned earlier on, actually wants us to do, if it ever says perform a test, that means we need to write the H0. H0 is that the block of flats is unchanged from the mean of 4 that we seen from previous experience, and H1, because it's two-tailed, is lambda is not equal to 4. Okay, so the key here, it says on a randomly selected month, 1 month period, the lift broke down 3 times. Okay, I just checked that our period's the same, but yeah, month time mean it broke down 3 times. Now, looking at it, that's we need to, 3 is not in the critical region, so because we would expect it to be either 0 or more than 9. So 3 not in critical region. So therefore, well, we do need to be careful here because of the wording. It's that the actual lift claim is that the mean is 4, and we've got kind of evidence that it's close to 4. So it's a kind of reverse logic really, that H0 here suggests that the lift alone claim is actually true, that the mean is 4. So not in critical. So this suggests lift for all claim it could be true, or is true. It's not really that the mean rate is 4. Okay. Just as a point of fact here, the null hypothesis always has equality on it, no matter what the wording of the original question. Okay, and alternative hypothesis always has either a not equal to or an inequality there. No matter, even when they kind of reverse the wording of the question, it's always set up like that. Okay, that feels like we've done a question, but in fact we haven't. We've got the some other stuff to do on this question, so let's have a look at that. This part D is actually quite similar to a question in if anyone uses the Pearson's Edexcel textbook on page 33, question 4. So if well-practiced students will have done okay with this, but it did cause a bit of confusion. It's one of these where you've got to unpick and you've got a bit of a Poisson going on and there's a binomial going on top of it, as we'll see. First of all, it says the residents in the block have a maintenance contract with List for All. The residents pay £500 for every quarter in which there are most free backed rounds. So I'm kind of underlining that. Let's work out that probability first of all. That's definitely Poisson, because they're talking about a rate of 2 times per month. But be careful, because we're looking at a 3-month period here. So what we want to be working out is what the probability during a 3-month period with Poisson 6, because it's 3 times 2, because it's 2 times per month, so it's 6 times per 3 months. And we want to work out the probability that, let's call it X, is, now we've got, if there are 4 more breakdowns in a quarter, the residents do not pay. So we want to find out the probability that there's fewer than 3 breakdowns. Let's just work that out. Probability if there's fewer than 3 breakdowns, and then work with that, because it looks like there'll be a binomial on top of this. So the inequality is going in the right direction. So one of the reasons why I've written it that way. What's the probability of getting 3 or fewer breakdowns? And let's look at where that is in the Poisson tables. So looking carefully, do be careful as you look through the columns here. It's easy to look at the wrong numbers. So we've got 6 here, and 3 or fewer is 0.1512. That's 0.1512. So if that happens during a 3-month period, if there's 3 or fewer, then that's £500 will be paid. In during 3-month period, if this happens. Okay, so obviously we're now looking over a whole year, because it says that somewhere. Yeah, find a probability to do not in the next year. So we're looking over a year's period. So we've actually got a few things need to happen here. So during a year, we do not pay more than £500. Either no money, is paid, or £500 is paid. It's one or the other. Do not pay much. So we're looking, so if we can find the probability of either of those, then we will be okay. And as I said, this is a probability of this happening during one 3-month period of £500. But what we're actually dealing with is, let's call it a different letter because we've already used X. So let Y be binomial with 4 trials, 4 3-month periods to make up the year, of probability of it happening 0.51512. So looking at this, so what the probability we're after is probability that X equals to 0 here, i.e. this never happens, that £500 is paid. So Y never occurs, because this 0.1512 is the probability that £500 will be paid during that 3-month period, or it happens one of the 4 quarters. So it's binomial. The probability of it never happening is 1 minus 0.152. So the probability that it never happens, that's 1 minus 0.1512. That's 0.8488. And that's every month no money is paid, because in every month there have been in fact more than 3 breakdowns during the month, so it's never happened. Or that in 1 month only that there's more than 3, and this happens. Oh, sorry, there's less than 3. So only 1 month it happens that there is less than or equal to 3. Okay, so I think I got the words slightly mixed up there, just to be clear. I don't want to stop the video and say something that's wrong. This number here means that 4 times that it's more than or equal to more than 3. Not more than or equal to 3, more than 3. 4 or more breakdowns have happened in each of the 4 quarters. Now the next number will be that only in 4 times there will be, in 4 months it will happen once. Okay, so that will be 0.8488 cubed times 0.1512, but don't forget the binomial coefficient 4. Okay, I think I'm getting the words right out here, but it is terribly confusing. It did cause quite an amount of difficulty in the question. Yeah. So when we work that out, 0.889. Okay, so is the answer when we work all of those together. So we've done the question. Just going to annotate this just in case I got the words wrong at any point. This represents probability that Px is greater than 3 has occurred 4 times. Or we can look in another way, Px is less than or equal to 3 has never occurred. Because I think when I've been saying it, I might have been saying it the wrong way around, and that would be terrible. And this represents the probability that Px less than 3 has occurred once only, has occurred once of the 4 times only. Or if we're looking at the other way, has not once, has occurred 3 times, in fact, not once, 3 times. Or probability x is less than or equal to 3 has occurred once only. And that would be the time when the £500 has been paid. So, quite confusing, and hopefully I haven't added to it by doing that question. Let's go on to the next question now. Okay, so it's always a bit of a relief after pulling through such a wordy question last bit to actually get to doing a bit of just calculations, a little bit of just not having to do much in terms of unpicking and interpreting. Here we go, we've got a PDF, okay, and the PDF, it doesn't tell us the value of k, it doesn't tell us the value of n, so I sense it's going to be a bit of a pure mathsy thing, and say a bit of a relief for some of us. It says find k in terms of n. Well, we're going to use the fact, because it does give us the range here, if we use the fact that the probability is equal to 1, so we can use the fact that some number between 1 and 0 is bound to occur, or the area underneath a PDF is equal to 1, we can use this information, 1 naught is equal to 1. So that just gives me k over n plus 1, x to the n plus 1, from 1 to naught equals 1. So obviously that just gives me k over n plus 1 equals 1. So, as I say, a bit of a relief after what we've just been through. K is equal to n plus 1. Okay, nice easy 3 marks. Did come out a lot quicker than what we did before. Ex in terms of n, well, Ex is equal to the integral of between 1 and 0 of x fx. So that's fk x to the n dx. I know k in terms of n, but we can always deal with that in a moment. So that's integral of 1 to 0 of k x to the n plus 1 dx. So that comes to add 1 to the power, so it's n plus 2, x to the n plus 2 from 1 to 0. So that gives me k over n plus 2, but we already know that k is equal to n plus 1 from here, and it wants it in terms of n only, I think. Yes, in terms of n only. So that's n plus 1 over n plus 2. Okay, nice. And then C, right, for C we're going to use the variance formula, I think. Find Ex squared, or no, Ex squared, we'll use a variance formula for part D. So Ex squared, it's going to be much the same as this, is going to be equal to 1 to 0, it's getting a bit repetitive now, but as I say, blessed relief after previous question, dx, so that's equal to kx n, x to the, it's meant to be x squared, n plus 2, from 1 to 0, so that's k, this will be an n plus 2 there, of course, as I integrate it, so that's sorry, I'm rushing this, aren't I? Just want to get through it. So that's not integrated yet. K x to the n plus 2 dx. So that's k over n plus 3 x to the n plus 3 from 1 to 0. So that equals to basically k over n plus 3. But as I said before, k is n plus 1, so it's n plus 1 over n plus 3. Okay, and then finally part D. Given n equals 2, find var of 3x. Well, the variance of 3x, first of all, let's be clear about this, is a formula for this, because it's a variance, that's 3 squared times the variance of x. So that's 9, the variance of x. And we also know that Ex squared will be equal to 2 plus 1, which is 3 over 5. And we know that Ex is going to be equal to, because n is 2, using this formula, that will be 3 plus 4. 3 over 4, so not 3 plus 4, 3 over 4. Okay, so therefore the variance of x is equal to Ex squared minus Ex squared, which is equal to 3/5 minus 3/4 squared, which comes to 3 over 80. But we haven't got that, that's variance of x. As we said, variance of 3x, as we've seen above, equals 9 variance of x. So that's equal to 27 over 80. Okay, somewhat of a relief after the previous question. That was not too bad. Okay, question 7, last question on the paper, I think. And this is a sampling distribution of medians. Right, so obviously we can call the sampling distribution anything we like. It doesn't really matter. We can call it. We could call them X and X there, and they could be. Obviously, the median is got to be one of these numbers: 10, 20, or 50. So we're going to have some kind of probability distribution here for our answer. So we've got to work out the individual probabilities for these. It'll take a little bit of work. It should be okay. Okay, so to get the 10, we're either going to have all 10s, well, that's going to be, the probability of getting a 10 is 1 out of 5, because we've got the ratios 1, 2, and 2. So that will be 1 out of 5 cubed, which is 1 out of 25. But that's not the only way of getting the median. We could also have a 10, a 10, and a 20. There's 3 ways of getting that, because the 20 could come at the front or in the middle, and that will be equal to, but then again we're going to have 1/5 squared, because we've got 2 10s, but we've also got 120, so that's 2/5. So that's looking like 6 over 125. Okay. Then we could also have, so we have 3 times those, we could also have 10, because if it's a median, remember the median's the middle one, we could also have 10, 10, and 50. Well, that's also going to have 3 times 1/5 squared, because we're going to have two 10s and 150. So that will also have a probability of 6 over 125. Okay, so adding all those together, we get 13 over 125. Okay, now that's the probability of getting a 10. 20 is going to be a little bit more to look for. Obviously, they could all be 20s again. That will have probability. There's only one way of doing that, but this time they've got a probability of 2/5. So that's 8 over 125. We could have, now one thing we do need is 2 20s, of course, so, well, that's not quite true, is it? Just realised what I've just said there. That's not true, but 2 20s and one other will definitely do it. 20, 20, and 10. The middle one of those in order will definitely be 20. Again, that will have 1 10, which is 1/5, 2 5s, which is 2/5 squared. It can happen 3 times because the 10 can come in any order. So that will come to 6 over 125. Okay, but we could also have 20, 20, and 50. That equals to, again, now 20, 20, and 50, that will be, because each one of these now will have a probability of 2/5. But again, it can happen in 3 different distinct ways, because we've got, we've got 50 could come in any order. So that is going to be equal to 8 times 3, 24 over 125. And as I just slipped out earlier on, there is another way of getting this, of course, is that we pull each one of them because 20 is the middle number. So that's 10, 20, and 50. Okay, now that will be again 1/5 times 2/5 squared. Okay, for the probability. Now, this is where you've got to take a bit of care because the number of arrangements that can be is 6. We could list them if you want: 2, 20, 50. So 10, 50, 20, 20, 10, 50, and so on. And then you'll find that there's 6 of them: 20, 50, 10, or 50, 10, 20, or 50, 20, 10. Okay, so that's a number of permutations of getting all of those. But for those of you who know about these things, that's a quick way of doing that is 3 factorial, which is 6 permutations. Edexcel don't do a lot of permutations, combinations, arrangements, that type of thing. But it wouldn't be that hard to list them all out. So that's 4, again, that's 24 over 125. So adding all those together, just notice that's 12 there. Remember that. 4 times 3 is 12. Adding all those all together is 48 plus 12, 60, which is 68 over 125. Now to get the 50, now we're in a funny situation here. There was quite a lot to do here. You could easily make a mistake like I nearly did here. It's tempting to just take the numbers away from 1. So we've got 68 plus 13 equals, take that from 125, and we get 44 over 125. And that will get you full marks in the exam. It's the kind of thing, if you've got no more time left on your hands, because it's the last question on the paper, then hopefully that's right. But of course, there's a lot that could go wrong. So I would check with the other one if I had time to check that it's actually all gone correct. And then hopefully, if we set our work out nicely, if we made an error like that one, then we'll be able to correct it. Okay, so let's have a look at the probability of getting 50. Obviously, we could have 50, 50, and 50. That's equal to 2/5 cubed. So that's equal to 8 over 125. But we could also have 50, 50, and 20. There's 3 different ways of getting that, and they've all got probability 2/5. So that will come to 24 over 125. And again, we could also get a 50, a 50, and a 10. There's 3 ways of getting that, but this one's got probability 1/5. So that comes to 12 over 125, which is 44 over 125. Okay, so that was that paper. It's taken a while. It's almost taken, this commentary is almost taken as long as the paper would take in the exam. But hopefully you found it useful. Sorry for the odd little glitch here and there. And that's it. Bye-bye.